we've talked about Kepler's three laws, but it's maybe kind of hard to understand what they mean without experimenting with it a little bit. So in this mini lecture, we are going to apply Kepler's first and second laws looking at two different types of simulations. There are a lot of really excellent free virtual online simulations that we can look at for physics and astronomy. You can also play around with this lab if you would like. Um, I've got this simulation linked within our engagement check for today. So here, this lab is called Gravity and Orbits, and I'm going to click on the button that says to scale. Here we have a black background and a bunch of controls on the side. We've got a star in the middle of our screen that has a mass that's the same as our sun. We've got a planet that has a mass the same as our Earth. So we can imagine that this is our Sun-Earth system. I'm going to click on the grid here, which brings up a nice background grid for us. And then I'm going to click on the path. And this is going to highlight the path of this planet around the star whenever I click play. So there we go. Now our planet is orbiting around the star. Okay, so the star and the planet, in this case our sun and our Earth, both exert a gravitational force on each other. Those gravitational forces are equal in magnitude, but opposite in direction. So magnitude is the size. Here, I've clicked on the gravitational force. Remember that a force is a vector. So the size of this arrow here represents the size of that gravitational force. The direction of those arrows represent the direction of that force. So these forces, these gravitational forces, are equal and opposite between two objects. So we've got the gravitational force that the sun exerts on the Earth, and that's pointing inward toward the sun. And then we have the gravitational force that the Earth is exerting on the sun, and that's pointing out toward the Earth. So those two vectors are pointing toward each other. That means that these are attractive forces. That means that the gravitational force between the sun and the Earth is going to want to try to bring those objects together. You might wonder, well, if there's this gravitational force between these objects, why are these objects not being pulled toward each other? Well, the thing is that in order for a planet to have a stable orbit around a star, that planet has to have a particular speed. The speed that that planet has as it's orbiting around the star gives it something called centripetal acceleration. And then it has something called a centripetal force. A centripetal force is that planet's mass times its centripetal acceleration. So if that centripetal force is equal to the gravitational force exerted on the planet by the star, then the planet can live in a nice stable orbit around the star. So if something happens to perturb that planet's orbit, to change its speed as it's orbiting around the star, then that can impact its orbit, and that can disrupt this nice stable orbit that we have of the Sun-Earth system or any planet. These ideas also can be applied for any planet around any star, not just those in our own solar system. We can see evidence of Kepler's first law right here. Kepler's first law says that all planets orbit a star in an ellipse, not a perfect circle. If the Earth were orbiting around the sun in a perfect circle, the radius of this orbit would be the same everywhere. But we see that the radius of this orbit when the planet passes right through here is smaller than the radius of the orbit on the other side. There are two terms we can use to describe the closest approach and the furthest approach from the sun. The closest approach to the sun is called perihelion. Helion represents the sun. Peri just means closest. And the furthest distance that a planet is away from the sun is called aphelion. So over here is where the Earth is going to be experiencing aphelion. Okay, so here was perihelion, its closest approach. Over here was aphelion, its furthest distance from the sun. And I'm going to pause here. Oh, let's go ahead and let it make one more lap, just a little bit further. And I'm going to pause it, and we can actually measure this difference between perihelion and aphelion. So here I have clicked up the tape measure. I can move it around. I'm going to place one end of it right here over the sun, and the other end of it I'm going to place right here at perihelion, okay? And well, we're going to round this number to 91,500,000 miles, okay? So at the Earth's closest approach to the sun, we are at a distance of 91,500,000 miles, okay? So I've written that down here. We're going to see that in a minute. At its furthest approach from the sun, what we call aphelion, the Earth is sitting at a distance of, let's call that 95,000 miles, okay? There's just a tiny bit of difference between when the Earth is at perihelion and when the Earth is at aphelion. Let's talk a little bit more about the Earth's perihelion and aphelion. So remember that perihelion was the closest approach that the Earth makes to the sun. And at perihelion, we said that our Earth was at a distance of, well, we're going to call it 91,500,000 miles. So 91,500,000 miles. So I have to multiply this number by another 1,000. So I'm going to say by another 10 to the 3 miles, because 10 to the 3 is the same thing as taking 10 times 10 times 10. 10 times itself 3 times, which is 1,000. So 91,500,000 miles. We're going to convert from miles to meters. Now I know that in 1 mile, there's 1,609 meters. And the miles cancel here and here, and that leaves me with units of meters. So this thing that I wrote right here, this little fraction, that's our conversion factor to take us from miles to meters. And you learned about this in lab 1 at the beginning of the semester, these conversion factors. So I take 91,500 times 10 to the 3 times 1,609. That gives me the distance that our Earth is away from the sun at perihelion. And that distance is going to be, we're going to round to 3 significant figures, 1.47 times 10 to the 11 meters, okay? And at aphelion, that's our furthest distance away from the sun. So let's say farthest. We were at a distance of 94,500,000, or times 10 to the 3 miles. So 94,500,000 miles times our conversion factor. In 1 mile, there's 1,609 meters. And that gives us a distance of, we're going to round again to 3 significant figures, 1.52 times 10 to the 11 meters. So the difference between these two, if I subtract the distance we are away from the sun at aphelion from the distance we are away from the sun at perihelion, that distance, that difference in the distance, is 5 times 10 to the 9 meters. And that's the same thing as 5 billion meters. There's a distance of 5 billion meters between when our Earth is at its closest approach to the sun and its furthest approach from the sun. Now, the interesting thing is that perihelion happens during January. We actually make our closest approach to the sun on January 2nd this year of 2021. So actually that already happened. Our Earth is closer to the sun in the winter time. and farther away from the sun in the summertime. So actually on, let's see, July 5th of this year is when we will achieve aphelion, our furthest distance away from the sun. So this tells us actually that the reason why we have seasons on our planet is not because we're closer to the sun in the summertime and further from the sun in the wintertime. It's actually the opposite of that. And this very, well, it might not seem like it, but actually pretty small difference between aphelion and perihelion for our Earth around the sun doesn't really impact our seasons at all. Now, we also learned about 1 AU, the astronomical unit. 1 AU is defined as the average distance between the sun and the Earth. Average distance between sun and Earth. So, and that is also equal to 1.5 times 10 to the 11 meters. So if we took the average of our 1.47 times 10 to the 11 meters and our 1.52 times 10 to the 11 meters at perihelion and aphelion, we'd get something close to our average distance between the sun and the Earth, which is what we define as the astronomical unit. I'm going to clear this simulation by clicking the little kind of circular arrow in the bottom right. And what I'm going to do this time is I'm going to put back up my path of the planet and the grid, and I'm going to make the sun twice as massive as it is now. And I'm going to leave the mass of Earth alone. So now I have a star that's twice as massive as the sun, and then I have a planet that's the same mass of the sun that's going to orbit around the central star. So now I'm going to press play, and this orbit is going to look a little bit different than the one we just looked at. Okay, so because this star is much more massive than our own sun, that impacts the orbit that the planet experiences as it's orbiting around the central star. So when you increase the mass of the star relative to the size of the planet, you actually can get more of an elongated orbit, more of an elliptical shaped orbit. So this orbit we see is much more elliptical than the orbit that we had for our own sun. And all we did was increase the mass of the star by 2. So we can see here, this is again another example of Kepler's first law, that all planets orbit around a star in an ellipse, not a perfect circle. And we can also see Kepler's second law. Kepler's second law talked about how when a planet gets really close to the star, to perihelion, that planet orbits that star much more rapidly than it does when it's at aphelion, its furthest distance away. And we can actually see that by, if I click on the velocity vector for the planet. So remember, a vector has both a size, that's the magnitude, how large it is, and a direction. Okay, so this arrow, the longer that arrow is, the greater the velocity, and the direction that that arrow is pointing is the direction of the motion of the planet at that instant. And so you can see that when that planet passes its closest approach by the star, it's moving much more quickly. It has a higher speed than whenever that planet is further away from the star. And that is a great example of Kepler's second law in action. The same thing happens for our Earth. Our Earth does orbit the sun a little bit faster whenever it's at perihelion than it does whenever it's at aphelion.